Hello everyone, it's November 19th. Hi, what a day. I had to I had to make a little trip earlier today and it was raining. Oh my goodness, it was pouring, right? And in addition to pouring, traffic was horrific. It took me more than 3 hours in total just on the road. Jeez. Alright, but we're back at it. An easy one again today. Hamming distance. I learned hamming distance many years ago, and I forgot what it is about. Have I done this before? I've done it back in 2020, July. It's like the recycle target is always July 2020. Anyway, so hamming distance between two integers is the number of positions at which the corresponding bits are different. Given two integers, return the hamming distance. Ah, I see. So I think it's going to be exclusive OR, and we need to count how many ones there are, right? So exclusive OR, and then count how many ones. There are an easier way to count how many ones. I mean, how many one bit? I'm just like turn it into a binary string and count how many ones. So it'll be something like this, right? So it'll be x exclusive or y, and we'll turn this thing into a binary, right? And dot count 1. I think we have a count. Not 100% sure. I'm guessing. Yeah, I think this shall be it. There we go. What did I do last time? Did I not use exclusive OR last time? No, I did. It's exactly the same. All right. Oh yeah, we're still gonna record it, but apparently this one is very simple. I want to see the discussion. There got to be a way without turning it into a binary string, right? That's what I want to see. If there's any way, I mean, there is way. There are ways. We can do like a shift, right? But then it will be a counter. But something like this. So that's the binary. So we're gonna say temp equals this, right? Temp equals this, and then we say while temp, and the result is 0, right? While temp, and we say rest plus equal to temp and 1, right? And then temp, we're gonna go right shift 1. And then we're going to return rest. Yeah, we don't have to do this. Yeah, let me try this one. I mean, let's be cheeky. I can just do 0 here, right? Rest and this, like this. This one should be right too. Wait, we're left shifting or right shift? It's a shift right. Huh? What? What? I don't, wait. Oh, temp equals. Gosh, come on. And just to prevent, let's just do this more explicit. Yeah? This one probably is slower. It's alright. It's alright. So, I mean, with these two, I still want to check the result. So this is I use binary string, right? This is a right shift to count 1 bit. Do we have another solution? Okay. Without exclusive OR. Ah, this is exclusive OR. Come on. Ah, okay, we can do that. Yeah, it's the same idea. Exclusive OR count bits. That's what we did. Brian Kernighan. Huh? Oh, there is. Wait. Number of set bits includes a result of loop 2, a result is not 0. Each iteration unset the rightmost bit and increment count of set bits. This can be done using an operation. This and this minus 1. Subtracting 1 from the number toggles each bit starting from the rightmost set bit. Yes. And ending it with n give us a result after unsetting the rightmost bit. It was the result after unsetting the rightmost bit. Yes. Then what? N minus 1. Rightmost bit got unset. Now n equals this. N minus 1, rightmost bit unset. Oh, shoot. So we use minus 1. Okay, so this minus 1, because I need to borrow. It's a borrow, boom. So once I do that, and I can end the 2, but these will be all zeros, so we don't care. And this don't care, so the result will be, oh wow. I knew it, right? I knew it. I knew that there got to be a easier way to do this. So exclusive answer plus equal 1. Ooh, oof. So good. So good. I mean, that's Kernighan, Brian Kernighan. All right, I'm going to use this one. Wow. Like, those people back then, they definitely needed to make it as, so this is Brian Kernighan. Brian, or he said it's called Brian Kernighan. I don't know why he has this hyphen in between. I mean, his name is Brian Kernighan. No, I'm not going to put hyphen. That's his name. Approach. So good that I will not remember it for sure. Right? I will not remember for sure. So basically, like this, and rest plus equal 1, and temp will equal to, will actually end equal to temp minus 1, and return rest. I'm going to add a little comment here. Unset the rightmost bit. Wow. See, that's the beauty of like doing it again, right? We'll venture into other other solutions and you kind of learn more, right? It's all about learning. Right? It's all about learning. Even though I'm gonna forget about it very soon, but who knows, right? Who knows? Maybe I will not forget about it, right? Maybe I will not. But anyway, so we're done with this. This is what equal what 7? It's 4, 4, 6. I'll vote this one. 461. So this one is 461. 461. All right, let's roll another one. Yeah, we skipped the bash problem yesterday because I just don't have the gana to do it. Man, no tengo gana hacerlo. Porque es estúpido. Sí, es estúpido usar bash por eso. Hay otros métodos. Es muy bueno, más bueno como Python, ¿sí? No es necesario. Sea como sea, vamos a ver un otro medio. Vamos. The computer is too slow. I have to say it every single time. As if when I say it, it can make the computer faster. This is ridiculous. What the hell is happening? I think it's dead on me. Detailed explanation of heat. Now it shows. Can I stop it? I think I can stop it. Difficulty. Wow. Living the life with a slow computer. This is how it looks like. That's the story of my life. All my laptops are slow. Well, because I don't change them when it's supposed to be changed, right? I mean, this one's not mine, so I can't really like change it. But even my laptop is the same. I always wait until the last moment to change. So at the end, they will be super slow. I like this one because it has a gigantic hard disk. I think it's a 1 terabyte, right? And the memory is 16 gigabytes. So it's good. It's good compared to my own laptop, which only have 128 gigabytes on the storage. Jeez, can't even do anything about it. I mean, I want to play Diablo. I don't have. I want to play the old Diablo, which is not supported on the newer Mac OS. So I have to use the what's called a boot camp, right? The Apple Boot Camp to install Windows on my laptop. So I tried to do that on my newer MacBook, but it didn't work because I don't have enough space to set up a boot camp partition. So I have to do this on this one because this one has a gigantic amount of hardware storage. But I think this one's just, I don't know, it's just old, super slow. Like I've been trying to get the drop down. Take a look, like it's ridiculous. I'm not sure. Like this is my. Hold on. Why are you not responding? Wow, this is annoying. Like seriously. Come on, man. What the hell? This is the memory usage. It's not that big. If something is hogging the CPU, is that why? Who is hogging the CPU? Nobody is hogging the CPU. Let me see. I'm gonna turn off some of my other apps because I know the live stream software is a hogger. That's like duh. It's gonna be a hogger. So I'm gonna turn off my email client, turn off Slack, turn off Spotify. How about that? Oh, didn't get to split. All right. Come on. Oh, I can change how many questions to show per page. This is ridiculous. Alright, so we did... I'm going to skip this one because I don't want to. Just don't want to do it. Course schedule. How about this? Alright, let's do course schedule. Lately, I've been learning using TypeScript. Man, that thing is dope. TypeScript is dope. I'll never go back to JavaScript. TypeScript is so good. It's like you code in Python for so long. Like we have all these type hints, right? But this is like you have to make it work. But TypeScript is so strict. But you can set the strictness that they will really force you to change stuff. I mean, JavaScript is notorious. I mean, I have been bitten by those. Like sometimes the value is an undefined, a null or whatnot, and you never know, and the app just keep rolling on, and it's just ridiculous. Like there got to be a way to check. And now with TypeScript, you can check. So I'm enjoying it. All right, let's do this. Oh, 3 hints. There are a total of number of courses you have to take. Label 0 to this. You're given an array prerequisites where prerequisites I equals AI BI indicates that you must take course BI first if you want to take course AI. For example, 0, 1 indicates that you take 0. You have to first take 1. Return true if we can finish all courses. Otherwise, I feel like I've done this before in an interview. Not a real interview. It's like the pre-screening of an interview. I feel like I've done this. And I failed. I remember I didn't do it very well. Let's see. Prerequisites 1, 0. Number of courses is 2. Alright, what does this mean? This means to take course 1, you should have finished course 0. To take course 0, have to if you can finish all courses. But so it is possible. If you can finish all courses. So basically this one will create a link. You have to take this one first, and then this, and then this, and then this, right? That means it's possible. This is impossible because to take course 1, you need to take course 0. But in case it's all 0, you need to take course 1. So we have a loop, right? So it is impossible. It's like a deadlock. Maybe you can use like graph. Say we have course 1, and we have course 0, and basically we can say course 0 leads to course 1. And in this case, we also have course 1 leads to course 0. And then we have a loop. So we can build a graph and then just check if there's a loop in it. And we know the algorithm to check loop, which is a slow node and a fast node. And if the slow node and fast node meet each other, then we are terminating. Okay, that's fine. That's fine. So what you're saying is we're going to build a graph, but it's not guaranteed that a graph will be connected. Because I can do, hold on. You have this number of courses taken, so from 0 to this. It didn't tell me the length of prerequisites. But I have all the classes. Wait, would it have all the classes labeled? All courses. Okay. All right. So I have a few questions, right? I have a few questions that I want to answer. So I'm just gonna whatever, and then try to answer questions. So we know this is gonna be 2, right? Can I do like 1, 1 and 0, 0? How do you handle this? Can I have the 2 the same? It didn't say if A and B has to be different. Oh, all pairs are unique. Okay, so this is not going to happen. Okay, how about this? 1, 2, and 3, 4. Right? And then we have 4 classes. Actually, no. It has to be 0, 1, 0, 1, and 3, 2. That's 4 classes. This one should be true. So we have like 2 disjoint graph. Okay. Okay. What do I do? Even if you build a graph, right? You build a graph, you don't know where the head is. Or the question becomes, given any node in a graph, you want to detect if it has a loop. Well, it depends on where the loop is. The loop can happen early on. And how should we approach this? Right, so eventually that's just going to be a loop. So I can build, right? I can build, or, I mean, if it's a graph, I can arbitrarily, you cannot arbitrarily pick anyone as a root. No, you cannot. It gotta be a node that nobody goes into. That is the root. And you have a node that doesn't go into anybody, then that is the tail. So to do that, we can, so like in this case, 1, 0, right? So we know 0 go to 1. So I say if a 0 gonna go to 1, and then 2 is gonna go to 3, right? So we can build this and see, okay, 0 only goes out. Anybody goes into 0. How do I check if anybody goes to 0? I mean, I can keep building, right? So 0, we have 1. 0 might have another thing, doesn't matter. But if 0 gets something goes into 0, right? So we're going to loop through all the pairs. And as we loop through the pairs, we can identify who are the root. The roots are the ones that will never appear on the first position, right? If you appear on the first position, you are not the root. The root is the one that does not appear on the first position. So we create the num courses, right? Create a set, and then we loop through all the prerequisites. Then we're gonna build the graph. And as we're building the graph, we also say every time we check the first value in the prerequisite, and then we remove that from the prerequisite from all the courses. So once the graph is built, we will have a set of courses that are guaranteed to be root. These are the root classes. And then for each root class, we run the algorithm of checking whether there is a loop. And we check all of them and return true or false. Okay, let's do this. We have an idea. What's the runtime? Good question that you shall ask. Currently, I don't know. Runtime, I mean, build is going to take, build a graph is going to take we have two. We have number of courses and prerequisites. So O prerequisites. Let's say that's M, right? M. So that's the prerequisites. So we build all the prerequisites, and then we have to check for the loop. So that's the number of nodes. So OM plus ON. I think that is the thing, right? All right. So we're gonna build. So we need a node. So class node a def initiate self. What do I need? I need a value, right? So that's when we know they will meet each other. So I need a value. So the value, and that'll be it. Self.val equals val, and I also need a self.next equals none. All right? It's a direct. It's a DAG. It's a DAG. So we're gonna build a DAG first, but we're gonna say the roots equal to a set range num courses. All right? It's gonna be the roots, and we're gonna build it. We say for actually it's post pre in prerequisites, because you have to take B in order, if you want to take A, you have to take B. So B leads to A. So B leads to A. Actually, I just do A and B. For A, B, and this, right? Roots, if A in roots dot remove A, right? And then we're gonna say, oh, hold on, I need a I need all these nodes to pre-populate it. Pre-populated. So root indices, right? That's root indices. And nodes is going to be this, right? For I in range num courses, I want to create a node with I, right? And then if A is in root indices, then we're going to remove it, so that cannot be the root. And then we're going to say, the next is going to be a, should we say none? No, it has to be this. It could be many children, right? So we just say nodes B dot next dot append, right? Dot next dot append. So append a new children. Hold on. Yeah, dot append. But that's a graph. Hold on. To detect whether the graph has, then we can bifurcate. What do we do if we bifurcate? Because it could be that one class is a prerequisite of many classes, right? So if if that class is a root, then we're gonna go and bifurcate. So every single one, and we just chase down every single one. That's fine. So the next, I don't know about next children. So children dot append append. Should we append? Should we or add? Because we might have duplicates in the prerequisite. I didn't say prerequisites are not duplicated. Let's see. I mean, what if I say 2 and I duplicate this, right? What if I duplicate? We have different values, 0 and this. So, okay, they're different. So, no worries. No worries. Actually, we can try again, just to probe the system a little bit more. This shall not allow either. Oh, this is allowed. Oh, the pairs are unique. So each pair is unique, which means there will be no duplicates here. So I can just put A, which is fine. But it is possible that we're going to have the thing pointing back to itself, right? But that's fine, doesn't matter. So no b.children. So this is the build. Now we've finished building. Then we are going to def check loop, has loop, check loop. So how do we check? We need a root, right? We need a root and actually we're not going to be doing this. Is this recursion or no? Well, it's not recursion. It's just hold on. Let me think. We're gonna go down, right? So we're gonna go down, and every time they're gonna be go forward 2 times. So go forward 2 times. So what if I hit bifurcation? That's the thing, right? That's the thing. If I hit bifurcation, that's when we need to. Okay, so I just move down, right? Move down. No, it doesn't work that way. Interesting. Like one path down, right? And then we have a prerequisite that can satisfy both classes, and we bifurcate. So we have a fast node going down. Now for a fast node going down, how do we check loop if it's not a linked list? Yeah, it's not a linked list. Huh. Oh, there's another way. Because each value is unique, we know the value. So if the value appears again, then that is a loop, right? So we check loop. Basically, we can just use one node. Yeah. We just use one node, right? We use one node. This one going to return a Boolean value. It'll work. So basically, we need to just keep calling this, and we need to also pass in like the path, right? The path. Yeah, so if it's possible, then it should be a one-way down, right? One way down. If it's not possible, then we're going to loop around. So we need to have a path, which is going to be a set, right? A set of integers, which is the value, right? Which is the value. So we're going to put the set. So let's say, we call the next node, we say if node.val in path, then return false, right? Otherwise, for child in node.children, right? In child in node.children, we say actually we can return If any of them is false, no. If any of them, no, hold on. All we want is to see if it's possible. So if one path down is possible, the other path down is not possible, that is not possible. So we need all of them to be true. We need all self dot check loop node. Oh, we have to upgrade path. Shoot. All right. So we're gonna add to the path first, and then call. Or no, we're gonna call it, and it will check if it's in the path. If it's not in the path, then path.add node.val. And afterwards, we are going to do say if check loop but if that's the case, when we unwind, we have to backtrack, right? Node.val, I add it to the path and I keep going. And then if this one's done, and we'll go back, I go down the other path. That's actually fine. Wait, is that fine? If I have path here, and I have the other path going and then meet here, does that count? That means we have to take this in order to take this. I have to take this in order to take. Hold on. I'm a little bit confused right now. So if we go like this, that is actually fine, right? Because this is one path, this is another path, that's fine. What is not fine is if it points back to any of the node that has visited before, right? If it points back here, but which is also fine, which means you have to take this path to take this. You have to take this, take this. So this is still a path, right? It will be a problem to pointing back to the path. So we do have to backtrack. So we can do loop, and once it's done, right? Let's say res equals to. All right, so this is a single path, right? Single path for each child. We go down that path, and then when that path is done, it will return when do we return true? Well, we need to return true. Oh, shoot. If there's no children, right? So if not path in path, if not node, so we go to the node, right? And if the node doesn't have children, if not node.children, that's the end. Then we return true. That's when we return true. And then we say path added, and then result will be self.check loop node path for child in this. So this one is going to be, if anyone is false, then it shall be false. So it has to be all true in order to be true. So all of this, right? Then path.remove node.val. This is where we're going to have to do backtracking, and we're going to return res. All right, so go again. So check loop, right? Check loop is going to be every single branch in the check loop. So we say if the next child has appeared in the path, that means there's a loop, and return false. If we go to the last node, that means this path is good, so return true. If none of these satisfies, then I'm in the middle of the path, and I add myself to the path, and then I check all my children, right? So I check all my children to check loop, right? Every one I check. I check. After I check every one, they will give me, say, a true or false or not. If one of them is false, it means there is a loop down the line this way. If one of them is false, then I know it's a false, because it has to be all. That may be a false. Then I have to remove myself from the path because I'm going to go backwards, and I return false. And actually that's not. We can end it early. Yeah, we should end early. You know what? That is not the best way to do. We can end it early. If we find that something is not a path, we just end it. Okay, if self.check loop node path, if not, right, then we just return false. We don't care. We don't care backtracking or anything, right? Otherwise, we keep going, and once going on done, I'm going to remove myself and return true, right? Now, can I put this one inside? It actually can. I don't have to check this because I can add myself and there's nothing. I remove myself, I return true. Perfect. So now we have this. All we need to do is for ri, root index in root indices. That's a set, and I will keep removing. So whatever is remaining is all the root indices. Then we just say self.check loop, right? Node is going to be nodes ri, that's a root, and the path is just going to be a set. So we're going to return all of them has to be true in order to be true. Okay? All right, so let's try testing this. All right, what do we have? We have first, it's 2, 1, 0. That is true. All right, and then we have 2, 1, 0, and we have 0, 1. Right, and that is a false. And we have 2. I give a 0, 0, 0, 0, and 1, 1. That is going to be false. And I have another one is 4. We have 0, 1, 2, 3. That shall be true. Okay. So this one we have num courses, some prerequisites. And this is can finish. Can finish. Num courses, prerequisites. All right. Roots is not defined. It's not root indices. Oh my god. It's completely reversed. What? What? That is not right. How? How is that possible? How is that possible? Come on, man. Come on. Okay, so before we return, I want to just print. Right? Let's print root indices. 0 is the root. I agree. 0 is the root. I agree. And then I'm going to check for ri in root indices. So only 0. So I'm going to check for nodes ri, so which is a 0, right? So 0 comes in, and node.val is 0 in path. No, it's not. And then path add in 0 for a child in this. Well, child is 1, should be. Oh, look at that. That is the problem. I thought that's the problem, but still not right. Well, without a pen, it's still not good. It's still not right. Huh? Yeah, that is a bug because I do have to put nodes inside. Nodes be our children, not a pen, right? So where did the false come from? So 0 coming in. I know this one is correct. And then let's say check loop. Let's print node.val and path. Let's kind of take a look how it looks like. Okay, 0, right? And then it's children. How? Print nodes. I have 2 nodes and they're different, right? So actually I can do for node in nodes, let's print node dot val and node dot children. That's first one, second one, that's exactly right. And then we pass in first the 0 and this, and it's not in, and if a child in node dot, oh, it's child. My God. There we go. Now we're good. Typo. What can I say? Typo happens all the time. Alright, so we passed these two, but I failed the middle ones. Okay. That's fine. Let's just take a look. So I return true. Okay, so again, we're gonna try to see what is the root indices. Huh? There's no root indices. Ah, yes, there's no root indices. Ah, so what do I do? If no root indices shall return false, right? And this one will return true, like nothing is inside. And all of this will return true. True. And so let me say root indices and nope. So we're gonna say how about len root indices. Okay, so I need to construct a more convoluted one. Let me construct a more convoluted one. So let's say 0, 1, 2, 3, 4. All right, so I have 5 classes. Right, let's construct this. 5 classes. 0 to 1. 0 to 3. 1 to 2. 3 to 4. 4 to 2. Oh, shoot. It's the other order. Jeez. Even making writing test cases difficult. 4, 3, 2, and 4. Alright? So that, I think, shall return true. But the same setup, we just change one thing. Instead of 4 to 2, we say 4 to 1. That's also true. But if I say 4 to 0, you see, that's going to be a false. If I can pass this, I'm going to write it. Okay, so let's do this. Let's do... Oh my God, what did you do, man? Okay, submit. All right, come on. Show me some. Show me some. Aye, timed out. What? How could we time out? Ridiculous. We must have hit. Oh, it's not timeout. Error. Expected false. But output is true. Alright. It's alright. I'll take a look. Not all classes is in it. I think I know. Not all classes in it. Not all classes is in it. I'm pretty sure if I check the root indices, it's going to be the value that's not inside. Right? 1, 2, 4, not inside. 7, 8, 9, 10. 10 is inside. 12, 14 is inside. 16, 18. Okay, so first of all, alright, so first of all, I'm going to check every single one. That's actually fine. Hold on, I think I'm going to change this. So root indices, right? So I have 10 to 0, so I put 10 in it. And if the first one is in it, I remove it. Yeah, I can just do set as this. If the first one's in it, we're going to remove it. Otherwise, and we're always going to put the second one in it first, right? So we're going to always put the second one first. So we're going to say root indices.add. Always put this. So by doing this, these are the values coming out, yeah? And I will check every single one. And then we have a true. Okay, let's draw it out. Let's draw it out. So 0, go to 10. 3 go to 18. 5 go to 5. Five go to 5. Holy guacamole. 5 go to 5. What if we don't remove? Like, why do we remove? Right? If we don't remove, then we'll pass, right? Yeah, we shouldn't remove. Every single one is going to be the root. Yeah. I mean, every single one has the potential to be the root. It might not be the actual root, but it's fine, right? We can always... Yeah, the thing is, like, with this situation, 5 and 5, but the reason I remove is because if I am initiator and I'm also something ending, then I'm definitely not the root, right? Unless A and B's are the same. Okay, I'm not going to do this. I still like how I do it, right? We're always adding and then we're also removing. But we're going to check. If A is equal to B, then we're going to return false immediately. Now the reason for doing that is this is just edge case, right? This is edge case because A and B, when they are the same, because it won't appear, right? Won't appear in the in root indices. Since it won't appear in the root indices, so this will throw us off. That's why I check this one first. And then everything else shall be as they are. No change is necessary. Okay, so we're basically just adding this line, right? We're just adding this line. For A and B, oh no, we actually changed quite a few. All right, we'll have to do that again. Let's do this again. All right. All right, let's go. Switching. Oh, I feel like we're gonna run again. Shoot. What is the problem this time? What? Empty. Empty case. Did they say it can be empty? Alright, my bad. My bad, I didn't see this. Holy guacamole. So what? I can do... So I'm talking about like we can do any value. Like we can do like 20 classes. But no prerequisites. That shall be true. Wait, what? Oh, has to be, wait, has to be one class with 0. Wait, what is the rule? If we have nothing, right, then it's required we have, so I think 2 classes. Can 2 classes work? What is the rule here? Number of classes. 2 is still good. But 3 class, but where did you draw the line? 3 classes no good? Three is good as well. But then why 20 is no good? Why can't I say I have 20 classes, but I have no prerequisites? What did you do earlier? Basically, this saying, this will always be true. That is another edge case. So why is our result cannot figure it out? All right. There'll be nothing. And the len root, no, this will be 0, so there'll be no root. Why will there be no root? Always pushing in, and then coming out at no root. So it has to be like larger than 0. Let's do this. Now we'll return this. So false. Because there's no prerequisite, right? And then if there's no prerequisite, we didn't add any root into it. Because there's no root. If there's no root, see, that's a discrepancy. If there's no root because I push root in and I remove root, right? So I kind of, it kind of just get you to think whether we shall it's like patching, right? Let me think. What will be the best one? I want to write the code simple. Like we can add the edge case checking for sure, but I don't like it. I don't like it. What if we just, record all the root, all possible roots, right? And we go through every one of them. And as we go through one of them, we can record, right? We can record. That sounds a better idea. So basically, we still want this, right? but we don't need to check this. We don't need to check this. So we'll always add. We do not remove. We always add root. We do not remove, right? And then we simply check. Say all of them has to be true, all right? And we're gonna have a global. We're gonna have a global, say self.dp. Actually, I don't need to do it here. I can just do it here. Self dot, right? So self dot dp equals. Doesn't matter. Equals. So do we have loop, right? Do we have loop? True means we have loop. False means we do not have loop. But that's not what this one is. This one true means no. No loop is true, right? So initially, we're gonna say everything is true. I can just say true times num courses, right? And then we're gonna say check blah 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 for this in root indices. Okay, fine. So we're coming in here, all right? Now we're not gonna passing node. Why do we passing node? Should just be indices, right? Should just be indices. Well, I can. But think about it. If I go, I'm gonna rewrite the whole thing. This thing can live inside. Yeah. So we're gonna live this thing inside. All right. So check. That is not node. That is ni, so node index, right? That's gonna int. Path we still need. So node index is your value. So that means I don't even need a value. What do you need a value for? Right? You don't need a value. If that's the case, I don't even need node. Why do you need node for? All you need is just a list. Right? This is just going to be a list. That's just going to be a list. For this, yeah, that's all the nodes. Right? We don't need a node. I don't need any of these. So it's going to be the start. That will be the indices. Right? DP is going to be this. And then when I check loop, that's fine. And I have the index, which is just call it index. We have a path. And we say if index, well, actually, let's start with none. Say if DP index is none, is not none, right? Then we just return DP index. Do we even need to return anything? We don't have to return anything, right? So we don't have to return. Why do we return? We do want to return. Return can make it faster. So we just say if DP is none, right? No, it's not none, we're just going to return it. End of the story. Otherwise, we say if index is in path, then DP index equals false, return false. Elsewise, then we're gonna add index, and we're gonna say for children in nodes index, right? For children in nodes index, we say if not, self.check loop child, no, so don't call it child, CI, child index, right? Child index. If this one is false, then I shall do the same thing. Right? If one of them is false from me, right? From me, if one path is false, then I just say dp index equals false, then break. All right, and I break it. I am going to break it, and I will have else. Else is if everything is fine, then I'm gonna say dp index equals true, right? And then we're gonna just return dp index, right? That's the logic. If it's not none, I return it immediately. If it is none, then I say if index is in path, if it's in, it's going to be false. I'm going to return. Which I can actually do it this way. If it's in path and else, right? All these will happen in else. And then at the end, we're always going to be return dp index. Which means if dp is none, right? Just further, if it is none, then I'm going to do this. If it's in path, we do this. If it's not in path, path added, we check the next index, and we just check. If any of those checking returns false, then I set mine to false and then break it. Otherwise, if everything is true, then index will be true. Then path and remove index as well. Remove index. And once it's all done, I'm going to return dp index. So that is check loop. So now we're going to AB this root indices.add. This is just make sure we don't have a duplicate. B. And nodes B dot append directly. Dot append A. We don't have to. Just dot append A. Once it's all done, now we're going to do this. All right, let's try it again. One more time. No attribute check, so we don't have to do self. Let's do this. Indices must be integers, not list. Oh, my bad. That says no more node. It's this. Has no check loop. Can I check loop again? Here, check loop again. There we go. There we go. This shall be right. Come on, we simplified it tremendously. Now we pass every single one. All right, come on, come on. There we go. There we go. This is it. All right, we went through many iterations. That's more iteration than I like. I went through like quite a few iterations on this. The final idea, the final solution is much simpler, right, than the one envisioned initially. The idea is to build graphs based on prerequisites, and then check whether any graph contains loop. Right? If loop exists, it's impossible to take all the classes. Now, initially, I created a new class, another class, to represent each node in a graph. But later on, I realized that this is not necessary because the node value is the same as the index, right? Index I assign for each node. Thus, all nodes can be represented by a list of lists. So that is, each element list is the node. Furthermore, we can use DP caching to simplify, right? To simplify the logic of checking loops. We say we cache whether the DPI, so DPI represents whether there is a loop if we start from position I. And I just realized I don't even need to use a list. I could just use a default dict, which I think will be saving on the memory, but I'm too lazy to do that. I'm maybe going to save some time as well, because it's going to take a long time, because if you think about it, I have 10 to the 5th. I'm going to have to build a DP for 10 to the 5th. I want to try it. Whether there is a loop if we start from nodes I, right? If we start from nodes I. So at the end, we also keep a set of all possible routes. We will go through each possible route, potential route, and if anyone leads to a loop, and it's impossible. Take all the classes. Alright, so I'm going to change this. So I'm going to go default dict from collections and import default dict. I'm going to do default dict. No, that's not DP. Oh, DP is going to be both gonna be default dict. All right. So this is gonna be default dict list. DP is going to be the default dict lambda none, right? And then I don't think I need to change anything. Add nodes B, yeah, I don't think I need to change anything. I just change these two lines, and the hope is by doing this, we are tremendously reducing the memory. So the memory usage is 17.7. Let's see if we can reduce the memory. Not really. So yeah, it's fine. All right, let's check. DFS. Topological sorting. Topological sorting. Detecting a cycle in a direct graph represented is inconvenient for implementing. First, transform it to the adjacent list. Of course, U is a prerequisite, then the adjacent list U will contain V. How do you do topological sorting? DFS. Let's go for DFS. We start from a node and keep visiting its neighbors. If at a time return to visit a node, there is a cycle. Otherwise, start again from another unvisited node and repeat the process. Isn't that the same? I feel like that's the same as what I was doing. So basically, we are going through every single one. So they eliminate one of the things, so they don't have the roots. So I'm saying they're doing more than they should. But it's fine. Not done and not acyclic, return false, right? So this is build a graph, which is fine. Acyclic, we're gonna do, if to do, we have a to do. What's a to do? Graph. To do is a vector of Boolean. If to do is true. Wait, what's to do? Build graph. To do, they all false, right? Done is all false. And then as I build a graph, graph G prerequisite second, of course. And then what? And then I say if not done not done, then I'm gonna check basically G to do, done, and I. And I'm gonna say if to do node is false, is true, then I return false. I don't understand this first part. Because initially you're all false. I understand that if it's done, right? If this one's done, then we'll return true. Otherwise, both gonna be true. Then for V in all my neighbors, I'm gonna check if it's acyclic. And if it's not, if there's a loop, then I return false. Otherwise, to do for to visit and nodes visited. To do is node to visit. Nah, I don't understand this part. I don't understand that. If to do, then return false. Hold on. Let me check the God. Alright, here's the God speaking. BFS. Yeah, I'll go for BFS. Degree. Using degree. That is to find the root. We have similar idea to find the root. So for I, for everything, for j and degree j minus equal 1. Oh, degree means how many nodes you're connected to, right? So the roots are the ones that don't have anything. They only go out, right? So they don't increment. So, but in that case, and we return len BFS. So we visit every single one, right? We visit every single one, degree j. So when I visited for j in GI, that's the neighbors. So for every single one coming out, I visit you, then I'll decrement your degree, right? And I say if the degree is 0, I will append that you become a new root. Then you will come out. What if the j is visited multiple times? Which is fine, right? Which is fine. And then eventually when they return len BFS equals n, because if there happen to be if there happens to be a cycle, what's going to happen? That means, yeah, what's going to happen if there's a cycle? It will go to j, right? So okay, so we start with j. Yeah, let me try this. Let's say just 0 to 1 and 1 to 0, right? So 0 to 1. So I say 0 will append 1, and degree on 1, oh, the recipient. So 1 will be 1, recipient will plus equal 1. And come again is 1 to 0. If 1 to 0, so 1 will add 0, and 0 will go 1, right? And BSS will be empty. BFS will be empty. So in this case, there's no root. There's no root. If there's no root, that's no good. So we want the root, the number of roots to be the same. So we're saying if there is a cycle, right? If there is a cycle, then we do not have a root. That's what it is, right? If there happens to be a cycle, then within the cycle, there will be no root. So I can have a root and keep going in. When I go inside the cycle, I can just do the same thing, right? We pick it out, and then the degree will be minus 1 until the degree becomes 0, and then I become the new cycle. So if I come in here, right, and then I will have degree 2, right, if that's in the loop. So minus 1, we cannot go here, and this will go in. This will go in, this will go in, this will go in. And then this will be here. And this minus, and it will go in as well. So in the other case will be the root is counted twice, right? So either there's no root, or you have some root gets counted twice. Wait, hold on. No, the root doesn't get counted twice. No. The root will have multiple degrees, right? The root will have multiple degrees. And if I decrement the degree, that will not be 0, right? And then we just end. Yeah, like imagine, right? Imagine we're going down a path, and then we hit a node that will initiate the cycle, right? Then that node will have degree more than 1, right? Because it's receiving something and it will be more than 1. So in that case, if that's the only path down, then that node will not become the root. And then that's the end. Oof. Using degree is interesting.